In this section, we'll be learning how to simplify radicals. We'll start by talking about what a simplified radical is, and then learn how to simplify radicals using the product property, and then simplify radicals using the quotient property. We'll also learn how to rationalize the denominators. So the first thing we need to learn about is when are radicals in simplest form. So much like a fraction is not in simplest form, let's say the fraction, for example, 2/4. So everyone knows that's not in simplest form, and a lot of times they say, well, it's not in simplest form because it's 1/2. But the real reason it's not in simplest form is because there's a common factor of 2. The fact that they both can be divided by 2 means that it's not in simplest form, and that's how we actually end up getting 1/2. So along the same idea where we have to simplify a fraction, we also have to simplify a radical. So radicals are going to be in simplest form when the number under the radical has no perfect square factors. So what this means is we should first look at our perfect squares. So our perfect squares are 1, 4, 9, 16, 25. You can see I'm listing numbers that I know the square roots of. And so I could go on forever, but I'm just going to kind of continue on like that. So what this means is that the number under the radical, so we're going to have a radical sign, and whatever's underneath it, if I can divide this number by a number off this list, then I'm going to have to simplify it. If I can't, then it will be considered to be in simplest form. And we haven't yet learned how to simplify. We're just going to decide if something is simplified. So the first example that I want to look at is radical 20. So I can decide if it's either not simplified or simplified, depending on if 20, which is the number under the radical, can be divided by any number on this list. Now the only number we don't count is 1, because 1 will divide anything. So I want to see if 4, 9, 16, 25, 36, 49, etc. If any of those numbers will divide 20, then it's not simplified. I would put it over here. If none of the numbers on this list will divide 20, then it is simplified. Well, since 4 divides 20, and 4 is a perfect square, so it's a perfect square factor, then that means that 20 is not considered to be in simplest form. And I'd put it over here in the not simplified column. An example of a radical that would be simplified would be radical 10. And the reason for that is because even though there are numbers that divide 10, like 2, 5, and 10, none of those numbers show up on my perfect square list. So 10 has factors, but none of them are perfect squares. So the square root of 10 would be considered to be simplified. So the first few examples that we're going to do, we're going to try to simplify just based on this fact. So we're going to figure out how would you simplify the square root of 20. Later on, we're going to learn 2 more criteria that need to happen in order for radicals to be simplified, but we're going to do that later. So at this point, I'm going to come down here and we're going to talk about the properties of radicals. So the first property that we're going to talk about is the product property. And what the product property tells us is that if you have a radical and inside you have 2 or it could be more items that you're multiplying, you are allowed to split those 2 items and give them each their own radical. Now they still have to be multiplying, but you're allowed to split them. And so we're going to use that to help us simplify on the next slide. We're also going to see that the product property can go backwards. So if you have 2 things that are being multiplied and they each have their own radical, there'll be times when it makes sense to put them under the same radical and multiply them. So at this point, we're going to slide down right here, and we're going to try to simplify these radicals. So I have the square root of 32. So I don't know the square root of 32 because it's not a perfect square. But I also know that it's not simplified because there are perfect square factors that will divide 32. 32 can be divided by 4 and 16. Now I want to pick the biggest one because this will allow me to simplify the fastest. So instead of taking the square root of 32, I want to rewrite 32 as the product of something. So I'm going to rewrite 32 as the product of 16 times 2. So if you look inside your radical, you're still taking the square root of the same amount. I'm still taking the square root of 32. I've just rewritten it as 16 times 2. But 16 times 2 is 32, so I'm really still taking the square root of 32. But now that I've created multiplication, according to my product property, I'm allowed to split and give each of them their own radical. So I can make it radical 16 times radical 2. And now that I have that, I know that the square root of 16 is 4. So that gets to come out of the radical, and I don't know the square root of 2, so that's my final answer. 4 radical 2. So this is a simplified version of the square root of 32. It's finally considered to be in simplest form when I get here. So let's try one more like this. So if I slide over to the square root of 24, I want to find a perfect square, so a number off of this blue list up here, that will divide 24. And I want to find the biggest number possible. So there is a perfect square that will divide 24. It's 4. And so 24 can be rewritten as the product of 4 and 6. So now the product property lets me split these each into their own radical. So now I have radical 4 and radical 6. And I know the square root of 4 is 2. I don't know the square root of 6, so that stays inside the square root, and that's my answer. On the next page, you'll do some additional practice on your own, but for the moment, we're going to jump back to this problem right here. So I have the square root of 9x squared. So 9 and x squared are being multiplied. So according to the product property, I could split them and give them each their own radical. So the square root of 9 times the square root of x squared. The square root of 9 is 3, and the square root of x squared would just be x for a couple reasons. One is that square rooting is the inverse of squaring, so they cancel each other out. The other thing is when you're finding a square root, you're finding the item times itself. So if I wanted to get x squared and I wanted something times itself, I would need x times x. So I know that's my square root. So at this point, you're going to try these 3 examples right here. Pause the video. When you're ready to check your answers, press play. So in this first example, I'm multiplying 25 and x squared, so I can split them and give them each their own radical. And then I know the square root of 25 is 5, and the square root of x squared is x. So 5x is my answer. On this problem, I'm taking the square root of 48, which I don't know the square root of, but I can rewrite that as the product of 16 times 3. Because if you multiply 16 times 3, you'd still get 48. The reason I picked these numbers is because 16 is the biggest perfect square that will divide 48. So even though 4 is also a perfect square that would divide 48, by picking 16, it means I'm going to have to simplify less in the end. And in a second, I'll show you why 4 would not get you to the full answer unless you simplify twice. Once I'm multiplying 16 and 3, I can give them each their own radical. The square root of 16 is 4, and I don't know the square root of 16. If you had picked 4 from the list, because 4 does divide 48, so it would be 4 times 12, then the square root of 4 is 2, and you're left with the square root of 12. The problem with this answer is that the square root of 12 isn't completely simplified yet, because there's a perfect square that divides 12, and that perfect square is 4, and 4 times 3 is 12, so I can split 12 again into 4 and 3. Now this square root of 4 is 2, but this 2 would be multiplying this 2, because there's multiplication happening here and here. So the answer to this, which is 2, would multiply this 2, which would get me 4 square root of 3. So you can see that you get the same answer if you follow the red path, but it takes you a lot longer than if you pick the biggest perfect square possible. So this would be like simplifying 10 over 20 by dividing top and bottom by 2 and getting 5/10. You'd have to simplify again, but if you had started by dividing top and bottom by 10, you would get 1/2 right away. On the final example in this set, because 36 and x to the 4th are multiplying, you can split them, give them each their own. The square root of 36 is 6. The square root of x to the 4th is x squared. And that's because if you wanted to get x to the 4th and multiply something by its exact self, you would need x squared times x squared to get x to the 4th. So your square root is x squared. On this example, so this time when we split square root of 25 and the square root of x to the 3rd, so I know the square root of 25 is 5. The problem with x to the 3rd is, if I'm trying to find its square root, nothing times its exact self will be x to the 3rd, because this is an odd exponent. And if you have the same thing here, your answer will always be even. So if you have the same number twice, you'll always have an even thing. So when it's odd, we can't really do it. What we have to do is split x to the third. And if you think of x to the third as x multiplying itself 3 times, I'm going to split it into x squared, because that's x times x, which leaves me with 1x left over. So now I do know the square root of x squared is x, and I still have a square root of x left inside. So anytime your exponent of a variable is odd, like let's say you had x to the 7th, I can't find that because nothing times itself would ever add up to 7. Then I would need to split it into the highest even number, which would be x to the 6th, which is always going to leave me with 1 left over. And now the square root of x to the 6th would be x to the 3rd, because if you multiply x to the 3rd by itself, if you can picture this, you'd have x times x times x, that's 3 x's, x times x times x, that's 3 x's. So in total, you'd have your 6 x's. So that's where your x to the 3rd is coming from. And then you'd have your 1x left over inside the radical. So in these next several examples, we're going to talk about the product property working the other way. So the first thing the product property told us is if we were multiplying, like up here, we were allowed to split and give them each their own radical. But the product property also works the other way. So what the product property will let us do is as long as these two things are both inside radicals, which they are, and they're being multiplied, which they are, I'm allowed to put them under one radical and multiply the two numbers. So instead of taking radical 6 times radical 6, I can make it radical 36. And I know the square root of 36 is 6. If I do that same idea on the next one, 3 and 6 are both inside the radical, so I'm allowed to put them under the same one and multiply, but then I'd really be taking the square root of 18. So now in that one, I don't know the square root of 18, but I can split 18 into its biggest perfect square factor, which is 9, and 9 times 2 is 18. Now I know the square root of 9 is 3, I don't know the square root of 2, so it stays inside. My final answer is 3 radical 2. So by kind of putting these two radicals together, I'm able to simplify. So you're going to pause the video and try these 6 examples. One thing that you want to remember while you're doing it is that as long as items are both inside a radical, you're allowed to multiply them together and get something new. If items are both outside a radical, like here 4 is outside, you could multiply it with anything else that's outside the radical. And so here 4 is the only thing that's outside. So to start this problem, I would bring 4 to the front, and then I can multiply 3x and x and go from there. So you're going to start by making one big radical with each of these, and then once you've done that, you're going to re-simplify by splitting it back up. Pause the video, press play when you're ready to check your answers. Okay, so on this one I had left you off here, so I can multiply x and get x squared. So now I don't know the square root of 3, so that's why 3 stays inside, and I do know the square root of x squared, which is x, so that comes outside to join the 4. On the next one, the 3 isn't under the radical, so that's just going to come out the front, and then I can multiply these two together, so that's where I get 7x squared, because x times x is x squared, and then y squared. So now I took these 3 pieces, and I split them into their each own radical. So I don't know the square root of 7, so that stays inside. I know the square root of x squared is x, and I know the square root of y squared is y. So that's my final answer, 3xy, radical 7. On this one, because the 7s are both inside, I can multiply them together, which gets me 49, and the square root of 49 is 7. Another way to think about this one is that if you look at the square root of 7, it's being multiplied by its exact self, and anytime something's multiplying itself, it's being squared. And square rooting and squaring are inverses, so they essentially cancel out, so you're left with just 7. So anytime you multiply a radical by the exact same radical, you're going to end up with just the number, because the squaring cancels out the square rooting. On the next one, 3 again is the only thing outside the radical, so it stays outside. 2b cubed times b is the square root of 2b to the 4th, so I split this. I don't know the square root of 2, so it's going to stay inside, and I know the square root of b to the 4th is b squared. So 3b squared radical 2. On this example, my 2 is going to stay out front, and then if I multiply, I'm going to get 5m to the 3rd, because that's m squared times n, m squared times m, and then n squared. So then I gave each of these their own radical. I don't know the square root of 5, so that's going to stay inside. I do know the square root of n squared, that's n. M to the third, I can't take the square root of it because nothing will multiply itself and make an even number. So I split it into make an odd number, sorry, nothing will multiply itself and make an odd number. So I split it into, still having 3 m's, I just made it m to the second, which is like having 2 m's, and then m, and the square root of m to the second is m. I don't know the square root of this m, so it's going to stay inside the square root. The next one, I split 8 and y to the 7th, and then I split 8 into 4 and 2, because 4 times 2 is 8, and y to the 7th, I need to make it even, so I could have the highest number is 6 y's, which would leave me 1 left over to get to my 7. The square root of 4 is 2, the square root of y to the 6th is y to the 3rd, and then I don't know the square root of 2 or y, so I put those under the same radical. So now in your notes, you're going to go back to the first page of your notes. So I'm just going to get rid of some of the stuff here. So we had already talked about the fact that radicals are not simplified if the number underneath the radical can be divided by a perfect square. So that's one thing that makes radicals not simplified. Another thing that needs to happen in order for radicals to be simplified is that you cannot have any fractions under the radical. So this isn't saying you can't have fractions, it's just saying that if you have a fraction, you couldn't have if you have a radical, you can't have a fraction in it, so that would not be okay. Radical 5 over 2 would be fine because the 5 which is in the radical isn't a fraction. The whole answer is a fraction, but the 5 is the only thing that's inside, and that's not a fraction. So we can't have any fractions under the radical. That's one thing. And then the other thing is, if you have a fraction, like here we have a fraction, there's a restriction, and that restriction is that you cannot have a radical in the denominator. So what this means is that while this answer is okay, even though it's a fraction, 5 isn't, but we're fine, what you would not be allowed to have is 5 over radical 2, because you're not allowed to have that in the denominator. The only real reason for that is that when you have a square root of a non-perfect square, if you go back to classifying numbers, those numbers are irrational, and mathematicians don't like to have irrational numbers as the denominator. So later on what you'll see is the way we're going to get rid of that is going to be called rationalizing the denominator, because we're going to be transforming this from an irrational number into a rational one. So we've already filled out the product property, and the product property allowed us to split or put together. The quotient property is actually going to work the exact same way. And so what the quotient property says is that if you have in a radical, if you're dividing a and b, they're under the same radical, you're going to be allowed to split them into each having their own radical, which will help us simplify when we have things like this that we're not allowed to have, because we wouldn't be allowed to have that fraction a over b. We would need to split them. So even though we have a fraction, we have now made it so a is its own number, b is its own number. So that's the first thing. And then the second thing the quotient property will let us do, just like the product property, is if we're dividing and they're both in a radical, we'll be allowed to put them under the same one, which might seem silly, but there'll be times where it makes sense to do that. So at this point, you're going to skip ahead to the first set of division problems on your notes. Okay, so these first few examples that we're going to do, if you look at all of them, we have a fraction inside the radical. So I have the fraction 16/25 inside a radical, 13/100 inside a radical, etc. And we're not allowed to have a fraction inside the radical. So we're going to simplify it by using the quotient property, which says that if two things are in the radical, you're allowed to split them. Now make sure when you split them, you can't relocate them. The 16 is in the numerator, so it still has to be in the numerator. The 25 is in the denominator, so it still has to be in the denominator. And when I do this, you're going to see like that one simplifies very nicely. It simplifies to 4/5. So even though I have a fraction, I don't even have any radicals, so I know I'm in the clear. On the next one, if I split it, I'm going to get the square root of 13 over the square root of 100. I don't know the square root of 13, so that stays in my numerator, but I do know the square root of 100 is 10. And that would be my final answer. So I have a fraction, which is fine, because inside the radical I have only 13, which is not a fraction, and my denominator isn't a radical, so I'm good to go. So you're going to pause the video and try these 3 examples. When you're ready to check your answers, press play. So on the this first example, we'd split it into the square root of 1 over the square root of y. So I know the square root of 1 is 1, the square root of y squared is y. So my final answer is 1 over y. Here I'd split it into the square root of 5 over the square root of 49. I don't know the square root of 5, but I do know the square root of 49 is 7. Here I'm good because I do have a radical, but it's in the numerator, and it's not a fraction inside the radical. So I'm good to go. And this one we split into the square root of 11 over the square root of d to the 4th. The square root of 11 I don't know, and the square root of d to the 4th is d squared. So now down here, you can see we have a problem. We have a fraction that has a radical in the denominator. So I need to cancel out the square root. So the inverse operation for square root, the inverse is to square it. So whatever that thing is, you would square it. Remember that to square something means to multiply by itself. So if I want to inverse the square root of 7, I would square the square root of 7, which means I would multiply by its exact self. But the golden rule of fractions says that whatever I do to the bottom, I need to also do to the top. So now in the denominator, 7 and 7 are both inside the radical, so I'm actually allowed to multiply them together. Now we get the square root of 49. And the reason that's helpful is because the square root of 49 equals 7. So I canceled out. I had a square root of 7 in the denominator, and I canceled it out, and I made it rational. So I started with an irrational number, and I've made it rational by multiplying top and bottom by the square root of 7. That's why it's called rationalizing the denominator. Now while doing this, I also had to multiply the top by the square root of 7, because that's what I did to the bottom. 5 times the square root of 7. 5 is outside the radical, 7 is inside the radical. So the best I can do is just show that I want to multiply them. 5 times the square root of 7. I don't know the square root of 7, so that's my answer. Now the reason that I can't simplify these 7s is because this 7 is inside the radical, and this 7 is outside the radical. And the product property and the quotient properties only apply when they're both either inside or outside. So this 7 that's inside cannot cancel with this 7 that's outside. So 5 radical 7 over 7 is my final answer. On this example, I have a radical 3b in the bottom, which I want to cancel. So I'm going to multiply by itself. I'm going to square it. So multiply by the square root of 3b, which means I also have to do it to the top. So now in the bottom, the square root of 3b times the square root of 3b. Everything down here is inside. So I can actually multiply it together. 3 times 3 is 9. B times b is b squared, so I'm taking the square root of 9b squared. Well, I know the square root of 9 is 3, and I know the square root of b squared is b. So by multiplying by itself, I got the square roots to cancel. I'm left with 3b. I went from irrational to rational. On the top, 2 is inside, 3b is inside, so I'm actually allowed to multiply these together this time. Now I get the square root of 6b. Now, even if I split them, I don't know the square root of 6, and I don't know the square root of b. So my final answer would be the square root of 6b over 3b. And these cannot cancel because 6b is inside and 3b is outside. So you're going to pause the video, try these 5 examples, press play when you're ready to check your answers. So here, to undo a square root of 3 on the denominator, we'd multiply top and bottom by square root of 3. And you end up with square root of 3 over 3. The square root of 3 times square root of 3 would be square root of 9, but the square root of 9 is just 3. On this example, you multiply top and bottom by the square root of x. So your final answer is square root of x over x. On this example, you multiply top and bottom by square root of 2. Now because 3 is outside the radical and 2x is inside, you can't actually multiply, so the best you can do is just put them together. So you end up with 3 radical 2x over 2x. On this example, multiply top and bottom by square root of 6, so you end up with 7 square root of 6 over 6. On this example, you multiply top and bottom by square root of 5a, so you end up with square root of 15a over 5a. In this example, you're allowed to multiply the 3 and the 5a because they're both located inside the radical.